we will solve the Schrodinger equation for the one-dimensional particle in the box. The time-independent wave function of a free one-dimensional particle is a linear combination of e to the power of ikx and e to the power of negative ikx. We now put this free particle in a one-dimensional box. Inside the box, the potential energy is 0. Outside the box, the potential energy is infinity. Therefore, this particle is completely confined inside the box. The mathematical equation is Vx equals 0, the potential energy is 0, if the position of the particle is greater than 0 and less than a. And the potential energy is infinity when x is less than or equal to 0, so in this gray region, or if x is equal to or greater than a in this gray region. Inside the box, it's a free particle, therefore we use the same wave function here, a linear combination of e to the power of ikx and e to the power of negative ikx. But also we know this, at the two boundaries, this wave function equals 0 when x equals 0 or when x equals a. This is to ensure the continuity at the two boundaries. So we'll use these two boundary conditions. Using inside 0 equals 0, we plug in x equals 0 here, and psi of 0 is equal to a plus a minus equals 0. Therefore, this coefficient a minus is equal to negative a plus. And then the wave function of the particle will have to be this a plus times e to the power of ikx minus a plus times e to the power of negative ikx. And we do know e to the power of I theta equals cosine theta plus I times sine theta. So we can prove this by doing Taylor expansion of both sides. And e to the power of negative I theta equals cosine theta minus I times sine theta. So we plug in these two equations here, and then we have this psi of x is equal to, again we expand the e to the power of ikx, e to the power of negative ikx. The result is 2i times a plus times sine kx, and a plus can be any constant, therefore we set a to be 2i a plus. This is just to simplify the expression of the wave function. And the second boundary condition is psi of a is 0. Again, at x equals a, the wave function must be 0 to ensure the wave function is continuous at this boundary. Therefore, psi of a is 0, therefore a times sine ka is 0. If a times sine ka is 0, we know ka will have to be an integer multiple of pi. It can be 0 pi, 1 pi, 2 pi, 3 pi, and so on. So therefore, we say ka equals n pi, and n is 0, 1, 2, 3, and so on. And psi of x is simply just a times sine. We're replacing this k with n pi over a here. And n equals 1, 2, 3. I deleted this 0 for a reason, because n cannot be 0. If we plug in n equals 0 here, we're looking at a times sine 0, and that means the wave function is 0. No matter where the particle is, that means the particle does not exist at all. So this is unphysical, therefore n cannot be 0. And also because the probability of finding the particle inside the box is 100%, so we can normalize this wave function. So we have to normalize this wave function inside the box. The limit is from 0 to a, and this psi x squared, the squared modulus of psi, is the probability density, and then this entire integral should be 100%. And we plug in the expression of the wave function right here, and we have a squared times the integral of the sine function dx equals 1. So this can be easily done if you know sine theta squared is equal to 1 minus cosine 2 theta divided by 2. And we just need to integrate this 1 minus cosine 2 theta and then divide the whole integral by 2. And we'll get 1/2 of a here. So if this is 1/2 of a, and then this uppercase A is equal to this is the dimension of the box divided by 2 to the power of negative 1/2, which is the square root of 2 over A. Again, A is the dimension of the 1D box. And we have now the wave function, and this is normalized. This wave function is normalized. It's square root of 2 over A times sine n pi x over A, and n is a non-zero integer. So now we're going to look at the shape of psi x in this picture. When n equals 1, we just plug in n equals 1 here. You have a square root of 2 over A times sine pi x over A. When x equals 0, we have wave function equals 0. When x equals A, we have pi times A over A. It's sine pi. Sine pi is 0 as well. When A equals 1/2 of A, the wave function reaches the maximum over here. What if n equals 2? When n equals 2, we're looking at sine 2 pi x over A. So when x equals 0 or 1/2 of A or A, the wave function is 0. So we see one node here. And then what if n equals 3? We see 2 nodes. So the number of nodes is equal to n, the quantum number, minus 1. And the more nodes we can see, the higher the energy. And how can we actually quantify the energy levels of the particle in the box? There are at least 2 different ways. One way is to use the de Broglie equation. The magnitude of the momentum of the particle is equal to h over lambda, and lambda is the wavelength of the particle, assuming this particle-wave duality. And if you look at the previous picture, lambda, the wavelength of the particle, is equal to 2a divided by n. So if we look at this, n equals 1, this is just 1/2 of lambda. Okay, this is 1/2 of the lambda. So 1/2 of lambda is equal to a, and then lambda equals 2a. And over here, this is 1 lambda, 1 wavelength. So when n equals 2, okay, we are observing the entire wavelength, lambda equals to a. And over here, this is the wavelength. The wavelength is 2/3 of a, and over here the wavelength is 2/4 of a. So really it's just the general equation is lambda is equal to 2a over n, and n is the quantum number 1, 2, 3, 4. And therefore we can just use the de Broglie equation, P equals h over lambda, and lambda is 2a over n, and therefore we have the magnitude of the momentum, nh over 2a. And this is the absolute value of the momentum, so the momentum is actually plus minus nh over 2a, where n is a non-zero integer, h is the Planck constant, a is the dimension of the box. Once we have the magnitude of the momentum, the kinetic energy is half mv squared, which is equal to actually momentum squared over 2m, and we plug in the expression of momentum, we have the kinetic energy expression, n squared h squared over 8ma squared. And also we can use the kinetic energy operator to obtain the expression of kinetic energy. Because we have the wave function here, it's the square root of 2 over a times sine n pi over a times x. Actually, this normalization factor is not important. It's not important if we are just trying to determine the kinetic energy of the particle. So we're going to apply this kinetic energy operator here to the wave function. So you can see this square root of 2 over a will appear in the end as part of the wave function. So really we focus on the sine function, and how can we take the second derivative of a sine function? The second derivative of this function is negative times n pi over a times n pi over a times this original sine function. So if we just evaluate the second derivative and multiply that by negative h bar squared over 2m, the result is n squared h squared over 8ma squared times the original wave function. And therefore, this wave function is indeed an eigenfunction of the kinetic energy operator, and n squared h squared over 8ma squared is the corresponding eigenvalue, which is the kinetic energy of the particle. And again, n can be 1, 2, 3, and so on. The momentum of the particle is plus minus nh over 2a because the wave function is a linear combination of two exponential functions, e to the power of plus ikx and e to the power of negative ikx. And both functions are eigenfunctions of the momentum operator p sub x, which is equal to negative ih bar d over dx. You can easily apply this momentum operator to this e to the plus ikx, and to verify that this is eigenfunction of the momentum operator with an eigenvalue of positive kh bar, and this guy has a eigenvalue of negative kh bar. So if we replace this k, we determined the expression of this k. This k times a must be n pi, therefore k should be n pi over a. So we plug in k equals n pi over a here. K equals n pi over a times h bar. H bar is the reduced Planck constant. So h bar is h over 2 pi. So we have h over 2 pi times n pi over a. We have nh over 2a. And this is the momentum of this wave function. And negative nh over 2a is the momentum of this e to the power of negative ikx wave function. So what's the physical meaning of this entire particle in the box wave function? This particle moves forward and backward simultaneously with a momentum of plus minus kh bar or plus minus nh over 2a, where n equals 1, 2, 3, 4, and so on. So we don't really know the exact value of its momentum because we don't know its direction. But we do know its kinetic energy. The kinetic energy of the particle in the box is n squared h squared over 8ma squared. So you can easily think of some real world examples. You can say, well, why don't we just try this? Why don't we try confine an electron in a one-dimensional box with a 1 nanometer length? So you just need to plug in the mass of the electron, 9.11 times 10 to the power of negative 31 kilogram. You plug in the dimension of the 1D box. You may think of a nanowire with a length of 1 nanometer. So you plug in A equals 10 to the power of 9 meters. And then you plug in the value of H 6.626 times 10 to the power of negative 34 joules second. And then this n can be any integer, 1, 2, 3, 4. This way you can easily compute the ground state energy of the electron and the first, second, third excited states of that electron as well.